Okay, 20103, lecture 5. Let's see, where did we stop? We're doing series parallel equivalence. Chapter 2. This is where we stop. Resistors in series. So let's move on. Resistors in parallel. Okay. It's the same derivation. Again, I don't expect students to memorize the derivation. The more important thing is you should know how to apply this equation right here. Even the equation is not something that you need to memorize. You can have it on your equation sheet. As long as you understand it and know how to apply it, that's all that matters. I always like to tell students that all of the techniques that we learn in this class, they're all tools in our toolbox. And it's up to you to decide which tool you wish to use. So again, multiple tools in your toolbox, different analysis methods. So here, resistors in parallel, I can find, let's see. I want to find Req, right? Req from Ohm's law, I can write as I into Req. So Req is V over I. Again, you don't need to write this down. This is just for explanation purposes. And then because it's a parallel network, the same voltage appears across all three resistances. And because it's the same same voltage, I can write I1 is equal to V over R1. I2 is V over R2. And I3 is V over R3. And I can either apply KCL or I can apply the voltage thing across all, same voltage across all resistances. I can get I is equal to I1 plus I2 plus I3. You plug in the values from above into this equation. You get V over Req is equal to V over R1 plus V over R2 plus V over R3. Voltage V is the same, cancels out. So you get 1 over Req, it's 1 over R1, plus 1 over R2, plus 1 over R3. Hence the reciprocals. So Req is the reciprocal of the sum of the reciprocals of all the resistances in that network. Okay, that's how we arrive at this equation for Req. All right, any questions? Two things, well, actually three things I'd like to point out. When it's a series network of resistances, we don't actually think about this, but our brain knows it. If you add a quantity to another quantity, we expect the result to be larger than that initial quantity. So if it's a series connection of resistances, the Req in that series network, that value for Req will always be larger than the largest resistor in that series network. Our brain already knows this. But we don't think about it actively. But it's a verification, right? Similarly, or conversely, in a parallel network of resistances, the resulting Req will always be smaller than the smallest resistance in that parallel network. Now that is something to think about, because if you solve a problem and your resulting Req is larger than the smallest value, that means there is an incorrect answer. There is an error somewhere in your calculations. So in a parallel network, Again, I repeat, in a parallel network of resistors, the resulting Req that you see here will always be smaller than the smallest resistor in that parallel network. It cannot be larger. If it's larger, that's an instant verification check. So you need to train your brains to automatically look for that error. Req cannot be larger than R1, R2, or R3. It will always be smaller than the smallest value. That's one thing, or the first point. The second point is kind of like a shortcut. If you have, so again, Req is smaller. Second point, if you have two resistances in a parallel network, two parallel resistors, the answer for that Req is simply the product of the two divided by the sum of the two. So if this was just R1 and R2, and you applied this equation, Req is the reciprocal of the sum of the reciprocals, it simply boils down to the product of the two resistors divided by the sum of the two resistors. Simply be R1 times R2 divided by R1 plus R2. Because if you solve this equation for R1 and R2 only for two resistances, that's what you would get. And hence, product of the two divided by the sum of the two. Yes. So the question being asked is, can we apply the trick to more than two resistors by breaking it down into into separate parts of two resistances each? And absolutely can. You can reduce. So as an example, you have R1, R2, and R3 here. You can first reduce R1 and R2, apply that shortcut. And once R1 and R2 is reduced, you now have one single resistor that is in parallel with R3, and you can apply that same shortcut again. But again, if it's if it's a complicated number like like 57 ohms times like 13, you might end up using a calculator anyway. So it's probably just easier to do it that way. This shortcut is if I'm just doing it manually, in my head without any calculators. But again, a good point. And the third is if you have a parallel network of resistances and they all have the exact same value. Again, parallel resistors with same value. Then the Req is simply that resistor value R divided by N, or the number of resistors in parallel. And you can try that with any number of resistances. 2, 3, 4, 5, 10, 50, 100, 1,000, always work. So again, where N is the number of resistors in that parallel network. Yes. Yeah. These are all, again, derived from this value of Req. So again, if you have 20 ohm resistors, and we will see that in an example in just a few slides. Let's say 100 ohm resistor, you have two of them in parallel. It'll be 100 divided by 2, 50 ohms. 100 times 100 is 10,000. 10,000 divided by 100 plus 100 divided by 200. And you still get the exact same answer. 100 ohm resistors, 3 of them in parallel would be 100 divided by 3. You can do it. 1 over 100 plus 1 over 100 plus 1 over 100. And take a reciprocal, and you will arrive at 33.33 ohms. Or 4 100 ohm resistors in parallel, 100 divided by 4, 25 ohms. And again, you can apply this equation. 1 over 100 plus 1 over 100 plus 1 over 100 4 times. and you take the reciprocal, you will arrive at 25 ohms. So again, no matter how many resistors you have in parallel, if they all have the exact same value, it is simply that value divided by n, the number of that resistors. There's 3 things to keep in mind. Okay, so baby steps completed. We'll move on to a larger analysis technique, which is finding the equivalent resistance if you have multiple resistors in that network. So in this case, not this case, sorry, we have A, B, C, D, 4 resistors, 4 examples. And you have open terminals at the far left. And those open terminals are where we are trying to determine REQ. Keep in mind that REQ for the same circuit will be different from different measurement terminals. If I was trying to, actually, you know what, let me come back to that point after I finish this first example. Okay. So example A, doesn't matter which terminals you are trying to find REQ at, you always start at the farthest end. At the farthest end. The farthest end is here, R4. And you start reducing as you move towards the front end of those terminals. So if I'm trying to find REQ at the far left, I start at the farthest end, which is R4, and I start coming back towards, from R4, I'm going to start coming back towards my measurement terminals. So when I start at the farthest end, I see R4. R4 is in parallel with R3, is in parallel with R2. 3 resistors in parallel. Okay, so my REQ in this case, I can reduce. And redraw the circuit in this manner. And as I go along in a schematic, I tend to rename, well, not rename, but I tend to label the resistors like this. So if my last remaining resistor was 4, I will name this resistor as R5. So R5 is the parallel combination of R2, R3, and R4. Make sense? Right? And then what can we say about R1 and R5? They're in series. So my REQ, that's a Q, is R1 plus R5. And that's it. Make sense? Any questions? So now, just as a side note, what if I was trying to measure the terminals across R4? So these are the open terminals on the left, right? It's simply implied in these examples that we are measuring the resistance at these open terminals. But if you're taking an actual measurement on your lab bench, you connect the circuit, and instead of measuring across these 2 terminals right here on the left, you connected it here. Do you expect the same REQ? Probably not. I would say definitely not, because the circuit is now different. So if I measure REQ at these terminals, and I start at the farthest end, and I move towards my measurement terminals, what do we see? R1 is not connected to anything. It's just hanging in the air. It's not part of the circuit at all. And the reason is there is no pathway for the current to flow through R1. It's an open circuit, so current does not flow through. It's a dead end street. If it's a dead end street, if it's hanging in the air, if a component is not connected back to the circuit, it's a dead end street. No vehicles can go through, no current can flow through there. It's an open circuit. So it may as well not exist as far as that circuit goes. Okay, so if you see something like this, then it's no longer part of that circuit. So the only thing that is left in this, well, not the only thing, the only things that are left in the circuit are R2, R3, and R4. Make sense? I'll take a 10-second pause. While you think over it, let me know if you have any questions. Any questions? Again, measurement terminals on the left, you have a different value for REQ. Measurement terminals on the right, different value for REQ. Yes. Well, I'll let you tell me. So the question being asked is, what if R1 was connected to the circuit? So let's see, what do we have? We're trying to measure REQ here. And again, R1 connected back to the circuit. What can we say about the relationship between R1 and R2? One end is connected there. The other end is connected here. So these two are in, no, parallel. Both terminals connected together, so they're in parallel. And if they're in parallel, then the total REQ in this case would simply be all four of them in parallel. But very good question. So again, the circuit as it is, you measure from a different terminal R4. R1 is open. REQ is simply the parallel combination of R2, R3, and R4. If there was a short between R1 and R2, now the other end of R1 is also connected to R2 and becomes R1 parallel R2 parallel R3 parallel R4. Three completely different circuits. Even though the circuit schematic looks the same, depends on your measurement terminals, basically where you're connecting your power supply, where you're connecting your ohm meter. Okay. So again, these are just conceptual things that students should keep in mind. Typically, I don't trick students, or I don't put something in my quizzes or exams which they have not seen before. There might be something that you have to think about, but other than that, there are no tricks. So this is not a trick. This is just a concept that students should be familiar with. Depending on the measurement terminals, the circuit is different. And that's what I'm trying to point out. Yes. Which one? R1 and R2? Oh, because R1 and R2 both have two terminals. And so they're connected, one terminal here, and the other terminal is going here. It's just drawn differently. But the other end is still being connected here to R2. For them to be in series, they should only share one terminal, not two. If they share both terminals, then they are in parallel. But did this example make sense to everyone? Okay. How about B? We take it step by step. Just because a resistor is on the diagonal or drawn in the circuit schematic diagonally, do not let it throw you off. Step by step. First of all, we start at the farthest end at R4. Again, I'm talking about circuit B. Okay. We start at the farthest end. Farthest end, I have R4. The next is R3. R4 and R3 are connected at one end. There is a third connection at that junction. The top end, R4 and R3 are connected, but there's a third connection at that junction. That means they are not in series. However, if I look at the other end of R4, it is connected to the other end of R3. So both R4 and R3 have connected terminals at both ends. So what does that mean? In parallel. So in B, what I like to do, if you see something like this, is you stretch out the node. Remember, theoretical circuit analysis, a dot is the same as a small dash, is the same as a small line, is the exact same as a very long line, right? So a tiny dot is the same thing as a very long line. So what I'm going to do is I'm going to take this point for R3 and I'm going to make it horizontal. I'm going to make it vertical. I'm going to stretch out that bottom node and stretch it towards the right. Okay, so I'm going to draw R3 like this. All I've done is I've taken this node at the bottom and I'm stretching it out towards the right. It's exactly the same. So this is exactly the same as this. No difference. It's just drawn on a diagonal instead of being drawn vertically or horizontally. So this is R1, R2, R3, and R4. And so I'm fond of the phrase, redraw the schematic in a way that makes sense to me. Okay. So I always advise students, always suggest you redraw the circuit in a way that makes sense to you. As long as you follow the basics and do not change anything in the circuit, you will arrive at the right answer. So redraw the circuit in a way that it makes sense to you, and then you will arrive at the right answer. So in this case now, if I want to find REQ, I start at the farthest end. Farthest end is R4. R4 is in parallel with R3. So R4 in parallel with R3, which would then be in series with R2. So I'll call this R5, R2, and R1. So this would be in series with R2, and that combination is in parallel with R1. I'll take a 10-second pause while you let that sink in. Let me know if you have any questions. Yes. 2, 3, and 4. Yes. Yes. Once you reduce R2, R3, and R4, you'll have one single resistance, and that would be in parallel with R1. Any other questions? Okay. Same thing with D. You have a resistor R3 kind of drawn diagonally. I'm going to draw it vertically. And this time I'm going to stretch it towards the left like this. If I stretch it towards the left, I get R3 as vertical. And then after that, it's straightforward. So in this case, if I start at the farthest end, what do I have? R2 and R1 are connected at just one junction at the top right corner. They are not connected at the other end. The other end of R1 is connected to R3. So R1 and R2 are in series. Okay. So again, I'm starting at the farthest corner. R1 and R2 share only one node. They do not share two. They're only sharing one node. They share, it's known right here. The other ends of R1 and R2 are not connected together. Call this R4. R4 is equal to the series combination of R1 and R2. So my REQ is R3 parallel R4. Make sense? We have values 3, 2, 1. Okay. Any questions? Straightforward enough? Okay. All right. So we learned about resistors in series, resistors in parallel. Then we applied those techniques to reduce a large network of resistors down to one single resistance. The purpose is we will apply this to a larger analysis technique where we introduce a source in the circuit. And we call that technique as series parallel equivalence. Again, going back to that most important point I said, all the analysis techniques that you learn in chapters 1 and 2 are built on top of each other. So we learned about Ohm's law first, then KCL, KVL, series resistance, parallel resistance, series parallel network of resistances. And now we introduce a source into that network of resistances, and we can analyze for voltages and currents using this technique called series parallel equivalence. Again, this is something I believe you have seen before, right, in physics. Okay, well, the idea is simple. It's a three-step solution. We first take the large network of resistors. Any source in that circuit, we take it out first. So once we take that source out, we have open terminals in its place. We find the REQ, or we determine the REQ between those open terminals, and we reduce this large network of resistors down to one single resistance. Once you have one single value for that single resistance, you apply Ohm's law. V equals IR. The source could be voltage, the source could be current. But once you find R, you have one known value, and then you determine R, you can find the third by applying Ohm's law. So is this your source? That's your circuit. You reduce it down to one single element. You find the voltage or current as the case may be, and then you expand it back up step by step in the exact reverse order that you compressed it. Okay. So the first step is reduce. Second is apply Ohm's law. Third is expand the circuit again. Let's take a look at this example so that it makes sense. When we start this, I'm going to remove the source. Let's put the source right here. Then I want to find Req between these open terminals. Oh, note about passive reference configuration. Current always flows from high to low. That's for passive components, resistors, capacitors, inductors. Voltage always goes from high to low, so it goes from plus to minus. The other side of that coin is that if you know the current direction, then the point of entry is always high, the point of exit is always low. So again, high to low, meaning if I was given the voltage polarity plus and minus, my current is going in this direction. The other side is if I was given the current direction, then the point of entry in the component is plus, point of exit is minus. That's an important point to note. So current always flows from high to low, except when it is a source. Okay, passive reference configuration refers to passive elements. A source is an active element. It is supplying energy. The source could be voltage, could be current, doesn't really matter. But current direction for a source is the opposite. It goes from minus to plus. Otherwise, our equations would never balance out. Okay, again, remember I said power in real life is never negative. We only attach a negative or a minus sign to that power in order to balance out our equations. So if it's a source, then a current for a source, reference direction for a source always goes from minus to plus. Okay. So if you were given a voltage source, plus or minus, the current is going from minus to plus. If you are given a current source, where is the plus and where's the minus? What's on the left? Minus. And plus on the right. Remember, I said when we begin circuit analysis, we have no idea what direction the current is or what polarity the voltage is. And this is an excellent example to apply that. We have no idea where the voltage is. We have no idea what the current direction is, right? The resistors are just given to us. The values are just given to us. Now it is our job to assume the voltage polarity across these resistances and to assume the direction of that current. But those assumptions are based in logic. So we have a voltage source, plus and minus. Which direction is the current going? Top? Sorry, is it going up or is it going down? It's going up because it's minus. So my current direction is up. I will label that as I. I'll label it as I or IS. VS is simply the voltage for the source, so VS. If it's going up, there is no other pathway for it to take except this. So right off the bat, I know the direction of the current going through or flowing through R1. It's going from left to right. Does that make sense to everyone? Again, it's an assumption on our part. I could assume it to go in the opposite direction, I would still arrive at the same answer, except my answer would have a minus in front of it. But logically, it just makes sense, right? If I know my starting point is this Vs polarity is given as plus at the top and minus at the bottom, a supply current always goes from minus to plus. That means that current I should be going up. If it goes up and flows through the circuit, logic dictates that my current I should go through R1 from left to right. Then it hits this junction right here. It splits in two. When it splits in two, we still keep following that same direction. And so it goes up or down through R2 and R3. I see down. Why the hesitancy? Even if it's a non-engineer, you should be able to say, right? It's going down, R2 and R3. And so it goes down in R2 and R3. And then again, logically following the same pathway, comes through here and combines back into I. Make sense? So this is how we determine, well, not determine, this is how we would assume current direction and voltage polarity. Okay. There's two more things remaining, which is the voltage, sorry, one more thing, which is the voltage polarity for all three resistances. Current always goes from high to low, plus to minus. Point of entry is plus, point of exit is minus. So for the resistors, R1, point of entry on the left is plus, point of exit is minus. Same thing for R2 and R3. Point of entry is plus, point of exit is minus, plus and minus. And now we have assumed and labeled the voltage polarities and current direction for the entire circuit. Yes. That's only for the source. Resistor is a passive component. It does not supply energy. So it always goes from high to low, plus to minus. So again, good question. How do we know? Well, we know it from the passive reference configuration. For a passive component like a resistor, always goes from high to low, plus to minus. Again, when you do this, you take it step by step. You practice this step by step. By the end of the quarter, this should become second nature, right? And that's why I have a lot of homework problems at the beginning, because these are all conceptual, concept related problems. We good on the setup of the problem? Okay, then let's find REQ. We have R2 and R3. R2 and R3 are in parallel. We combine it into one resistance. I'm going to call this as R4. R4 is the parallel combination of R2 and R3. The parallel combination of any two resistances is the product of the two, 30 times 60 divided by 30 plus 60. So 1800 divided by 900. Is that right? 30 plus 60, 1800 by 90. Oh, 90. 20 ohms. Someone do this on a calculator and let me know if I'm correct. Thank you. And so REQ is R1 plus R4. $30 ohms. Yes. Yes, we are just trying to find. So the question being asked is, sorry, I interrupted. Go ahead, finish. No, that is if we just measure from the other side of the circuit. Yeah, when you are measuring from this side, if you're trying to find Req, then R1 is part of the circuit because a measurement meter would be connected here. So it is part of the circuit. All right, so where was I? Oh, Req. So we now took our network of resistances and we reduced it down to one single resistance. Okay. So V equals IR. I have Vs equals I times Req. So I can find I, plug in the values. What was it? 90 volts. Gives me 3 amps. That's the second step. When you apply Ohm's law. All right, let that sink in. Let me know if you have any questions. So far, so good. So now we have found the total current I flowing through the circuit. Now we expand it back up again and we apply that value to the resistors. Okay. So again, we know our I. I is the same current that flows through R1. So we can calculate the voltage across R1. Again, we are expanding the circuit. And so VR1 is simply I times R1. So it's 3 into 10 gives me 30 volts. Any questions? Make sense? Right? Now, at this point, we have two options. We can either apply Ohm's law again and find the current, find the voltage across R2 and R3, or we can apply, anyone? Yes, we can apply KVL. We have 3 voltages in the circuit. We know 2 of them. We can find the third by applying KVL. So here's the distinction. If a question asks you to use the analysis technique of series parallel equivalence, it's a larger method, right? The points of the points for those methods will be assessed based on whether the student can actually take a large network of resistances and reduce it down to a single resistance. You find the voltage and current first, and then you expand it back up. Now, within this problem or within this analysis technique, you will apply Ohm's law, you can apply KVL, you can apply KCL. That makes sense, right? So within this technique, there are other sub techniques that you would apply. You can choose whichever one you want to apply. That is fine. So points will not be deducted if you choose KVL or if you choose, Ohm's law. Yes. So we are talking about series parallel analysis technique. That technique involves reducing a resistance network down to one single resistance. So if students should show me that they are able to do that, and then you expand it back up again after you apply Ohm's law. But while you are expanding that circuit again, you can apply multiple techniques, KCL, KVL, Ohm's law. So that would be fine. You can choose whichever technique you wish to apply inside that larger technique. So as I was saying, now we have an option to find the voltage across R4. We can apply Ohm's law Again, because it's the same current I that is flowing through R4. I is not flowing through R2 and R3. I is flowing in the parallel combination of R2 and R3. Important thing to keep in mind, because I splits into IR2 and IR3. Okay. R4 is hypothetical. It's not real. R4 is hypothetical. That is how the circuit sees it, electrically speaking. And so in order for us to be able to solve it, we combine R2 and R3 into R4 on paper. But when you combine it, it's one single resistance, and I, the same current I, flows through R4. And that's why we can calculate the voltage across R4 using I. So VR4 is I times R4. 3 times, what did you say it was? 20, 60 volts. We can also find it from KVL. From KVL, I know minus VS plus VR1 plus VR4 equal to 0. Minus 90 plus 60, sorry, plus 30. So VR4 is 90 minus 60. Or sorry, 90 minus 30. You get the same answer. So once you have the voltage across the resistances R2 and R3, you can apply Ohm's law again and find the current for both of them. So IR2 is VR4 divided by R2, which is by, what did we have? 20, 30. 2 amps. And then IR3 is VR4 divided by R3. 60 divided by 60, 1 amp. Yes. 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 Question being asked is, why is VR4 the same for both? The answer is because they're in parallel. To take that point a little further, VR4 is a result of R2 and R3 acting together. Okay, it's not as if you remove one of those resistors, you would still have the same value for VR4. No, then the value for VR4 would change. Okay, across a parallel network of any components, the resulting voltage is due to all of those components working together. If you remove any one of those components from that parallel network, then the voltage will change. Oh, we're already at 11 o'clock. Didn't even realize. Okay, we'll stop here and pick up here on Friday. The announcement I was going to make was I will be here next week. Quiz on Monday. I typically take the bus and come to, hold on.